So EasySpin is a MATLAB toolbox. It runs on top of MATLAB. If you start up MATLAB, you will have a command window where there's a cursor that blinks and you can do basic calculations there. In order to install EasySpin, you go to the top ribbon, click on Set Path, and point to your browser. Go open a file browser, add folder, and then point it to where you have downloaded the zip file from an EasySpin website and unpacked it. I downloaded it into my C drive in ES 2023 in this subfolder here. And then inside the subfolder of the EasySpin you download, you will have 3 folders. One contains the documentation, one contains the actual EasySpin code, and the third one contains a host of examples categorized in lots of different subfolders. This is an excellent starting point for you to learn how to use EasySpin, just starting from examples, and you can then start and modify those examples, adapt them to your needs. In particular, I point to this subfolder called Photoexcited, where you'll have, is it the right folder? I think so. That should be the folder where we have the examples. Right, in order to add a folder to your path, you have to select the EasySpin subfolder and then press Select Folder, and then it will show up as an additional folder on your MATLAB search path. This is the list of folders that MATLAB looks for when you type in commands in MATLAB. And you click Save, and then you should close, and you should be all set. If you type now EasySpin in the command window, press Enter, it will print out information about what EasySpin version is installed. I'm using a fairly recent version here. It tells you where the folder is, and it also gives you information how to access the documentation locally. You can either click on the link here, or most easiest, you can just type EasySpin doc. So if you type EasySpin space doc, a MATLAB internal browser will fire up and will give you an overview of EasySpin. And you will have some basics on the top left. We'll have tutorials about how to simulate all sorts of EPR spectra. And in particular, again, I want to highlight the topic of today, spin-polarized systems. There's information on pulse simulations, also a link to the examples, then a link to the core functions here, and then a relatively short, compact summary of some EPR theory that you might need for your day-to-day work. So this is kind of how you get how you can help locally, and this is in my suggestion as the preferred way of obtaining help in EasySpin. Just typing EasySpin doc and the help will fire up. And this will always be the version that you have currently installed. All right, so for those of you who have not had experience with EasySpin before, we'll start off with a simple example using an nitroxide radical. I'll click here in the top left, generate a new script. And starting out, we're going to clear our workspace, typing clear, and also type CLC to clean out the command window. So there's nothing printed here. And then we need to start defining our spin center. And if you start with an nitroxide, we of course we have to first define which spins are participating or which we're interested in. So we call this sys, just as a generic name for like spin system. We could call it something else if you wanted. Sys.s equals 1/2. So we're looking at an electron spin 1/2. This is entirely optional. If you don't specify it, EasySpin will assume spin 1/2. Then we're going to add the nitrogen nucleus, since that nucleus is resolved in EPR spectrum through its relatively large hyperfine coupling. Sys.nux equals 14N, so nitrogen 14. Then we will add a G values for this for the electron spin, and we are going to provide the 3 principal values of the G tensor or G matrix. Typical values could be 2.0085, 2.0065, 2.023. And finally, we have to provide the hyperfine coupling between the electron and the nucleus. So sys.a equals, and some typical values will be 20, 20, and 100. in units of megahertz. So this defines and tells EasySpin about the magnetics of the spin center. Now, we've added only one nucleus. There might be other nucleus. Of course, there are other nuclei which have small hyperfine couplings that are not resolved. And in order to model these two in a summative fashion, you can add an additional convolutional line broadening. It's called sys.lw for line width, pp, which stands for peak to peak. And we're going to choose a value of 0.5. This is in units of millitesla. This is how you define a spin system. And if we fire up the documentation with EasySpin doc in the command window, there's more help about how to define spin systems here under basics. So for example, if you click here, you will see there is sections for every type of magnetic interaction that we typically include in EPR spectroscopy. And most importantly for today, there's also documentation on the zero fill splittings. And the value, the parameter here is D, or D, the underscore in D frame. All right. So now we've defined the spin center. This is the molecule that gives us the EPR spectrum. Next, we need to define the type of experiment we're doing. In this case, today, we're going to focus on solid state continuous wave EPR, but EasySpin also supports liquids EPR and pulse EPR and has quite an extensive support for pulse EPR. All right, so the CW EPR experiment is defined in an analogous way where you give some name that kind of collects all those parameters, a dot, and then provide standard names for these various parameters. So let's call this X for experiment, microwave frequency of 9.5 gigahertz. We could add, yeah, I think that's all we need. The rest can be used from its default values. So in order to simulate the spectrum, you call a function called pepper, simulate EPR spectrum. And you have to provide pepper with at least two pieces of information. The first one is what type of spin system you're looking at. And the second one is what type of experiment you're doing, X. And now if you run this code here, and you can do this by clicking the button up here, or pressing F5, or alternatively, click this button here, run section. EasySpin will simulate the spectrum and plot it as well in a separate figure window. I am docking this now. There's a little arrow here that allows me to dock this into the MATLAB GUI, so I have it handy all the time. So this is how you do a very basic simulation. Now you can also do other things. For example, you could plot the energy level diagram. And for this, we're going to start a new section that starts with 2% with 2 percentage signs and is highlighted with a blue ribbon here on the side. The advantage of these sections is that you can execute them separately. This is just like cells in a Jupyter notebook if you have experience with Python. So we're going to see if we can plot the energy levels for this system. Now the function for this, the EasySpin function, is levelsplot. And if you typed the parentheses and you press tab, you will get contextualized help on the EasySpin function. So here we can see that the first input levelsplot requires information on the spin system, which we have. The second input is a shorthand for the orientation or define theta angles. Let's put the magnetic field along the z-axis of the molecule. Third input is the magnetic field range. And we can go from 0 Tesla to 600 millitesla. And finally, an optional input is the microwave frequency. We're going to use 9.5 as a prototype, the typical one. Okay, if I run this now with either pressing Control Enter or, yeah, there we go. Oops. either pressing run section or run, or pressing Control Enter, I obtain the levels, a Zeeman level plot. And you can then zoom in, for example, here, and then clearly see that we have 3 transitions that are going between these pairs of levels. We have like 3 levels at the bottom and 3 levels at the top. If you mouse over one of these transitions, indicated in red here, it will show on top, it will tell you that's the transition between the 3rd and the 4th energy level as counted from the bottom, from lowest energy up, that it occurs at 442.55 millitesla, and that its relative intensity is 1.0. And similar for the other ones. Levelsplot is a very useful function to get a feel of how the spin system behaves in a magnetic field. So going back to the simulation and running that section again, pressing Control Enter or clicking the button here, Run Section, we can again get the spectra. Now, EasySpin allows you also to adjust a lot of simulation parameters that tell EasySpin how it should simulate and how accurately it should simulate the spectrum. And one of these settings is actually it's called opt.output, that will allow you to get EasySpin to return you 3 separate hyperfine transitions. So opt.output equals separate. And if you provide this opt for options as a 3rd input to Pepper, and you run this again with run section, you will see that you get a spectral plot that shows the 3 hyperfine manifolds, so m sub I plus 1, m sub I 0, m sub I minus 1, separately. And this is also this is pretty useful for instructional purposes. We get a better insight into your spin system. Finally, as you can see, we can actually now turn this off again, go back to the summed spectrum. You can see this is already showing a field modulated CW EPR spectrum. You can turn off the field modulation to get the absorption spectrum. In order to do that, use exp.harmonic. And typically the detection harmonic is the 1st harmonic. So if I use this, nothing will change. And if I set harmonic to 0, and I run this now, you'll see we get the clean absorption spectrum. I can again set opt output to separate, and we'll see the 3 separate transitions. Opt output, this is the current syntax, but our plan is to change that a little bit in the future to have more granular control of what is being plotted separately, either transitions or orientations or species, and so on and so forth. All right. This is a brief overview on how to do a CW simulation, but EasySpin would be pretty useless if you couldn't import and export your import experimental data, fit them, and then export the results. And I'll give you a brief overview how this is done. Again, let's start a new section here. I'm gonna close this figure, or just clear the figure, clear the workspace. Here we are. I have already saved in this folder an EPR spectrum before, and we can load it using the function EPR load. This is a EasySpin function. It supports all sorts of file types, older Bruker formats, newer Bruker formats, as well as Magnetech and other active spectrum and other companies. So EPR load, and then you provide the file name. And one of them, that's the one I've stored, has this file name, and it's a DSC file or DTA file. It's a current Bruker format. And then I'll ask EPR load to return me the magnetic field vector B and the spectrum. And then finally, I can just plot these, plot B and the spectrum. Let's see if this works. Voila, there it is. Here is a admittedly synthetic data set of a nitroxide radical with a little bit of noise, and the field vector as usual in millitesla, as is the default field unit in EasySpin. Now, in order to save a spectrum, all you need to do is call the function EPR save. And EPR save, again, if you open and close parentheses, press tab, we will see the inputs. It takes a few parameters, the file name, so my file dot DTA. Next, it takes the x-axis, which is in our case the V field, the y-axis, which will be the spectrum. Then you can add a title that will be stored inside the file, nitroxide simulation, let's say. And you can also store a microwave frequency. So that might be important as the most important parameter when you want to reuse this data. And if you run this, then your file will be stored in that folder shown up here. So this EPR load and EPR save are the functions to get data in and out. But as usual, you can type EasySpin doc in the command window. You'll get the browser, and then the first section of the basics user guide is data import and export. That explains things in detail. It also tells you how to import from Microsoft Excel or from simple text formats. All right, now, once you are able to import spectra, now it would be a good time to start thinking about plotting. All right, I'm going to start a new file here, clicking the plus button here above. Always start with clear and clear command line and loading the spectrum. So this is our situation. Let's say our task is to fit the spectrum. We'll have to provide esfit. EasySpin has a function that's called esfit that can help with that. But in order for esfit to run, we have to provide it with several pieces of information. First of all, our initial guess of what this spectrum is due to. And that's called a sys0, 0 indicating the initial part. So spin 1/2, including 1 nitrogen nucleus and 14. Some estimated G values, 2.008, 2.007, or 6, and 2.0023, and some estimated hyperfine values, let's say 20, 20, and maybe 80, and an estimated initial line width, which could be 0.7. Of course, we also have to add information for the experiment. There's a microwave frequency, which is 9.5. And there is a field range, which we have to provide in x-dot range. So the microwave frequency in gigahertz, and the range is going to be millitesla. And, we loaded the magnetic field data array. And so the simplest is just to pick the smallest value and the largest value from that vector. And in order to fit this spectrum with a model, we also have to make sure we tell EasySpin about the number of points stored in the spectrum. That's x dot endpoints equals. And how many points do we have here? There's this MATLAB command for that. It's called numl, number of elements of this spectrum. Okay, so we have information for the experiment, information for the initial guess for the spin system parameters. Now we need to provide information about how much this fitting algorithm is allowed to vary any of these parameters. And we're going to store that in a separate structure, which I'm going to call varysys. And let's say we want to vary the first 2 G values. We say varysys.g, and we're going to provide how much we're allowing to vary them, maybe by 0.01. And the third G value we're not allowing to vary, so we're setting it to 0. The hyperfine values, we keep the first 2 frozen and let the second one vary by, let's say, 30 megahertz. Again, I'm trying to annotate units to make sure that everything is well documented. Finally, we also let the line width float, and we let it float by a 0.3. So that sets us up with all the information needed to start fitting. So esfit is now the function that performs fitting. And if you go again between those 2 parentheses and you press tab, you will get information on what to provide. First, the experimental spectrum, about the SPC. We loaded that in line 3. Second, which simulation function we want to call. And for solid state continuous wave EPR, it's the pepper function. You have to add an at in front of that to point esfit to that function. They will call it. Next, you have to provide the initial parameters to the function. And if you remember, pepper takes up to 3 input arguments. So we have to provide a list of 3 inputs, or 2 if you don't have options. And the first input would be the initial value for the system, so since 0. And the second input would be the initial value for the experiment parameters. Next. So these in curly braces, these will be used as the inputs to pepper when it's called. Next, we'll have to provide information about how much these parameters can vary, or which parameters can vary. And we've defined that before in this varysys function, varysys structure. We're not varying anything in the experiment at this point, so we can just drop it. We don't have to add any vary exp here. But you could, for example, if you had some uncertainty about the microwave phase, you could include the microwave phase as a fitting parameter and have that fitted as well. But in our case here, we just have spin system parameters we want to fit. And that's basically all it's needed to get it running. So let's start this. And what you will see then is a relatively large GUI starting up. This GUI allows you interactive control over the fitting process. So on the top left, you have a list of the fitting parameters, and there's a checkbox which ones are allowed to float during the fit. It gives the name, the start, and the lower and the upper value bounds for the fitting ranges. You can select different starting points. You can generate a random starting point within those lower and upper ranges. And so there's a bunch of controls. It tells you also that the function is pepper. Here's on the top right. You can select the fitting algorithm. You can fit either the data as is, basically the spectrum as recorded, or you can fit the integral of the spectrum, which would be the absorption spectrum, or the double integral, or the derivative, or even the Fourier transform. And picking these different targets changes the error landscape, sometimes in a beneficial way. You can also include some baseline fitting. In the vertical axis in EPR spectroscopy is typically irrelevant. So it doesn't matter whether this is on a scale of 10 million or on a scale of 0.01. As long as we fit the spectral shape, the fit, we consider the fit successful. So therefore, EasySpin includes an auto scale option. So it automatically scales the fit, the simulated spectrum to fit the experimental spectrum. You will see here a plot of the RMSD, the root mean square deviation history as the fit progresses, and a log at the bottom here. And you can also save fit parameter sets and export them to MATLAB's workspace. So I can evaluate the function at the start parameter set and see how far off we are. Well, it looks we are quite a little off. The hyperfine coupling is too small, the line width is too broad, and so on. And if you click start fitting, it tells us that it's running optimization. And you can see the root mean square deviation plots starting to move. And you will see plotted on top of the experimental data a red trace and a green trace. The red trace represents the current simulation, and the green trace represents the best simulation so far. You can stop the fitting at any time. Then you can save a parameter set. You click Save Parameter Set, it will show down here. And now you can pick a different algorithm, let's say Levenberg-Marquardt, and then start fitting. As you can see, this fitting algorithm started again from the previous from a center point, and it didn't get very far. So every fitting algorithm has a different search range, and some of them might be good and work well, and others might not work that well. So if you then look here down in the log window, you will see a plot, a printout of the goodness of fit. After the fit is finished, it will tell you the RMSD, the noise standard deviation, the chi-square of the fit. It will give you the fitted scale. It will print out the correlation matrix, and it will give you errors. You print out the strongest correlation values here. And this way you obtain some information about the errors associated. They're also printed here on top in a table. So the best values for each parameter are shown in green on the best column. Standard deviation is next to it. And then you have the lower and upper bounds of the 95% confidence interval. So these are the numbers you want to then quote in a publication to indicate what is your statistical error in these parameter fits. So esfit as a GUI, but you could also just run it from the command line. So if I close this GUI now, and I just ask esfit to return me a fit result by prepending this, and then press run section, you can see that it now actually runs the fit in the command window without any plotting. This tends to be a little faster, but obviously it's not as interactive and visual. In order to stop this, you just have to press Control-C. All right, this was a brief overview of how EasySpin works. It's script-based, as you can see, with some user interface, graphic user interfaces. And I hope for those of you who have never used it before, this was helpful. I suggest we just then move on to part one of simulation of spin-polarized EPR spectra. Claudia, take it away.
Okay, so what we're going to do in the rest of the workshop is go through a couple of examples of spin-polarized EPR spectra and how you can simulate them and how you can use EasySpin to understand your spectra better. Before we start with that, since we know that some of you have not worked with spin-polarized systems or transient EPR before, just a very brief introduction. So the systems we're going to look at starting now are systems that are typically generated by photoexcitation. So one example of this is, for example, triplet states. So most organic molecules, if you excite them, they go to an excited singlet state, and some of them have efficient enough intersystem crossing to form a triplet state, which will be spin-polarized. And that's one of the states we're going to discuss. Then if you have a donor-acceptor system, their photoexcitation can be followed by electron transfer, forming initially a spin-correlated radical pair, which can then recombine to give a triplet state. Another process that involves photoexcited paramagnetic states is singlet fission, where you generate pairs of triplets which are strongly coupled, so you can describe them as quintet states, or they can separate then their individual triplet states. So these are all systems that you can now easily simulate with EasySpin, and we'll go through all of them in more detail in the following. So how do you get the spectrum of these states? So usually the first thing people do is run transient EPR. So this is a continuous wave EPR experiment, but has some differences to standard CW EPR. So essentially what you do is you sit at the single magnetic field, you continuously irradiate your sample with microwaves, and then you record your EPR signal as a function of time after a laser pulse. Then you repeat this at a couple of different magnetic field positions, and this gives you a 2D spectrum like the one shown here. So how do you do it technically on an EPR, Bruker EPR spectrometer? There's two ways to record transient EPR. You first turn field modulation off, and then you can either detect the signal using the diode in CW mode, or you can use what's called transient mode, where it uses the quadrature detection system for pulse EPR to get both in phase and out of phase contributions, and also one of them will then give you this 2D spectrum. What you have to do in both cases is synchronize your laser with your spectrometer, so you can define the time axis with respect to the laser pulse. Typically, these photoexcited states are relatively short-lived, so the timescales go from hundreds of nanoseconds to microseconds and very rarely milliseconds. Then once you have this 2D spectrum, you can extract different slices. So if you extract slices in the field domain, you can get your spectrum of the paramagnetic state that's generated by photoexcitation at different times. If you look at slices at the single magnetic field, you can study the dynamics of that photoexcited state. So what we're going to talk about today is if you extract a spectrum at a specific time after laser excitation, you get this 1D spectrum, which you can then simulate to learn more about the state that generated the spectrum. So what you can see here is that some features in the spectrum are negative and some are positive. So I said that we turn field modulation off, so that's not the reason for it. The reason for it is that most of these photoexcited states are generated with a non-Boltzmann initial population, which means that some of the transition will be in emission, so the ones that go down, and some of them will be in absorption. So that's what's typically indicated by this absorptive emissive arrows that are shown for transient EPR spectra. Then another thing that people should be aware of is that laser light is polarized. So if you don't depolarize it, you will have photoselection effects, because depending on the orientation of the electric field vector with respect to the optical transition dipole moment of the photoexcited state, you will select different orientations of the molecule. This will affect the EPR line shape, because not all of the different orientations of the molecule will contribute equally. And this is also something that we can now simulate in EasySpin, and we'll show you how to do that in a little bit. Okay, so going back to the spin polarization, the reason these different sublevels aren't populated according to Boltzmann distribution, but have a spin polarization, is that the different mechanisms are typically selective for one or more sublevels. So for example, for intersystem crossing, you're selective with respect to zero field levels, and then that translates into energy population differences at high field that determine the appearance of your spectrum. And as we will then hear later on in Matt's talk, you can also have different spin polarizations for photo-induced electron transfer processes and singlet fission. Okay, so before we start with the example, just a brief overview of how or what's new and how you can simulate these spin-polarized systems. So as we've seen, the thing that you really need to define in this case is the initial state, so the population distribution. For this, there's this new initState field, which is a Celery and takes a state input, which can either be a population vector or a full density matrix, and then a basis keyword that specifies the basis in which you're defining the state. There are a couple of different options. I'll just give a brief overview now, and then we'll talk about each of them in more detail with the examples. So the default one is the uncoupled Zeeman basis. So you can specify your density matrix in that basis. So for example, for a pair of radicals, that would be alpha, 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 beta, beta, alpha, and beta, beta. So you can define your density matrix, and then EasySpin will simulate the corresponding spectrum. The other option is to use the coupled basis. So again, in the case of two coupled spin 1/2, that will be T plus, T0, T minus, and singlet. And here you can again define a population vector. And for spin-correlated radical pairs that are generated from a singlet precursor, we also have the shortcut singlet. The other possible basis is the eigenbasis of the spin system. Again, you can give a population vector and then specify eigen as the basis keyword. In this case, the populations are ordered by increasing energy, which is something you need to be careful about if you use the eigenbasis for simulations. Again, there is a shortcut for one common example where you would use the eigenbasis to define spin polarization, and that's a triplet state, which is just populated in the T0 level, for example, by recombination from a singlet-borne spin-correlated radical pair. Then the next option is zero field. So you can define your populations in the zero field basis. Again, they're an increasing energy. And this is what most closely matches the way EasySpin was working up until now for spin-polarized systems in either the exp temperature or the sys-pop inputs. So you would use this, for example, for triplet states or quartet states where you know the population distribution at zero field, and then EasySpin will internally convert those populations into the high field populations and calculate your spin-polarized spectrum. Another similar but different basis that you can use for triplet states is the XYZ basis. So in this case, you just define the populations of the three TX, TY, and TZ states. This is essentially equivalent to zero field, but instead of having to worry about the energy order, you can just define your X, Y, Z values, and then depending on your sign of DNE, you will automatically take them into account correctly to simulate the spectrum, and that will also make it easier for specifying these populations in any publication. Okay, so now let's start with some of the examples. So the maybe easiest example, and the one that I've been showing in these 2D plots, is a photoexcited triplet state. So let's define a spin system. So in this case, we don't have an nitroxide, so spin S is 1 and not 1/2. And then in this case, we want to specify the zero field splitting interaction. So typically you can do this with two inputs, which define D and E in megahertz. And then we'll add some kind of line width. And then for now, let's just specify the experimental parameters. So microwave frequency. And then in this case, I don't think EasySpin quite manages to automatically get the field range. So we just add that. And then, since we don't have any field modulation in transient EPR, we'll set the harmonic to 0. So then we can have a look at what this gives us. Okay, so now we see a spectrum which is complete in absorption. It has a couple of different features which correspond to the different orientations of the magnetic field in the zero field splitting interaction frame. But as you can see now, it's all full in absorption. So if we wanted to make it a spin-polarized photoexcited triplet state, we now use the initState input. And the most convenient basis for triplets is the XYZ basis. And then we'll define a population vector which contains PX, PY, and PZ. So let's, for example, assume that we have equal populations of the X and Y levels and no population in the Z level, which is what you would get, for example, for anthracene or other similar systems. So if I do that, now we get this spectrum here, where part of it is emissive and part of it is absorptive. So then, as Stefan has shown you before, we can try to understand better where that all comes from by using levelsplot. Let me just set up the figure. We'll plot this spectrum here. And then define orientation. We can start with Z and then use levelsplot, which are a spin system. This orientation that we've selected, we want to see the levels from 0 to 500 millitesla, and then we can use the frequency we've used for the spectral dissemination. Okay. So if we run this now, we get this energy level plot, which for the triplet has the 3 different levels. At zero field, you have the Z, X, and Y levels, with the Z as the lowest level, in this case with the positive D value. And then they split apart by the electron-Zeeman interaction. And you can see that for this orientation, you get two different transitions. And then we can also try to simulate the spectrum for this orientation and try to plot it on the same plot. Just give me a second. Okay, so now you can see that if we just consider this single orientation with magnetic field aligned with the Z-axis, we get these two transitions, one emissive, one absorptive, which correspond to these outer features in the spectrum. So why are they emissive and absorptive? This is also something that levelsplot is very useful for. So we've defined populations of 0.5 for X and Y and 0 population for Z. The way zero field populations translate to high field populations is for the state that corresponds to the axis aligned with the field, the population stays the same. So we'll have 0 population for this Z level, and then the population for the other two levels will split equally. So we'll have 0.5 and 0.5. And that then means that we'll have this emissive transition here and absorptive transition there. We can then also look at the other orientations. We'll have X, Y, and Z. So now we have all three different orientations. For each of them, we have contribution of two transitions, which in this case are emissive at low field and then absorptive at high field. The other thing we can do is look at the contribution of the two different transitions. So one that's relating the MS0 to MS-1 and the MS0 to MS+1. So again, that's something you can do by setting the output to separate. And plot this and then plot this one as well. So now you can see that there's this green contribution, which comes from the MS0 to MS+ transition, and then the blue contribution that is the MS-1 to MS0. Then if you extend the field range to go down to 0, you can see that now we have three different transitions contributing to the spectrum, because now for orientations that are not quite along the axis, you start to have allowed transitions or not completely forbidden transitions between the MS-1 and MS+. And this is this feature that is simulated here. Okay, so this is how you can simulate triplet states. But then, of course, you can also go to higher spin states. So if we think about coupling this triplet state to a radical, then what we get in the case of strong coupling would be a quartet state. So let's have a look at what that would look like. So we have quartet states, so S is 3/2. Then we can again define zero field splitting. So typically, if you have a triplet state that then forms a quartet state with a radical, the D value is 1/3 of the contributing triplet state. So let's try a smaller one than before. let's add a line with, and then again, let's see, and field range. And again, we want the zeroth harmonic, so absorption spectrum. Okay, and so that's what it would look like if we don't define an initState. So that would be the Boltzmann populated quartet states. So where does this spectrum come from? So we can again turn to levelsplot. Let me just copy part of this and quicker. And start with the Z orientation and just look at levelsplot. And I code it differently. Okay, so now we have these 4 levels, and if we zoom in at a low field range, so 0 to 10 millitesla, we can see that at 0 field they start off as 2 pairs of degenerate levels, which then split apart at higher fields. And in this case, we can have all of these transitions. If the quartet state is generated by photoexcitation, we can again define the populations in a 0 field basis. However, since, as we've seen, at 0 field 2 states are degenerate, we need to take a little bit more care in how we define this in initState. So typically you want to specify the density matrix in this case and calculate what that would look like in the uncoupled basis. So if you look at the literature and you have a triplet which has a population distribution of similar to what we were using before, almost equal population of X and Y and 0 population of Z, that would translate into population of the quartet 3 halves, so plus minus 3 half states of Px plus Py over 2. And then the plus minus 1 half states would get populations of 2/3 times Pz plus Px plus Py over 6. Okay, so now we have our populations. Now we need the corresponding states. So again, you can look this up in the literature, and you can find how you define the different quartet states. And then in order to do this in EasySpin, we can use a very useful function which is called ZG matrix, which helps you build up states depending on whether you're coupled or it gives you a transformation between coupled and uncoupled bases. In this case, you're coupling the triplet and the radical state. So spin 1 and spin 1/2. And then we're interested in quartet states. So we're gonna have this function return the information for the states with overall S 3/2. And then the other 2 outputs are these ones. And then if you look at the third output, that gives you the contribution of the different coupled states. So these are the triplet MS values. These are the spin 1/2 values. So you can use this to build up your 0 field splitting states for the triplets. So just quickly do that. So you'll have the T minus R plus. So that's the 5th one here. Plus 2 times the 0 R minus, which is the 4th one. And then all divided by square root 3. And then we'll have something similar, but with the second and third states to give us the ±1/2 quartet states. And then we'll have the sixth one. That will give us the stochastic. And then we can define here our cis initState in the uncoupled basis. So we'll just calculate the density matrix by using the states we've just defined and the zero-field populations. So the populations are then B1/2, B3/2. Okay, typo. Okay, so if we do that, now we get again a spin-polarized spectrum, which looks a lot like the triplet. But if we again look at the contribution of the different transitions, you can see that we now have 3 different contributions. So between the -3/2, -1/2, +1/2, +3/2, and then also a smaller contribution between the 2 central states. And you can also then play around with zero-field splitting parameters and see how this contribution changes as you go to larger zero-field splittings or smaller ones. Okay, so slightly more complicated for quartet states, but still possible with EasySpin. Then next thing, or the last thing that I'm going to show you is how you can simulate photoselection effects. So I'll show that on the example of a triplet. So let's just briefly get the triplet again. We'll have zero splitting D value of 1000, E -15 megahertz. And then again, we'll use line width, and then again, we want it to be spin polarized. So in this case, I'll pick small population Px, no population Py, large population Pz. And again, select the XYZ basis. Then turn field modulation off, so I set X harmonic to 0. And then let's see what this gives us. So this is the triplet, or a similar triplet to what we had before. And then now what happens with photoselection? So as I briefly mentioned in the introduction, how much different orientations of the molecule contribute to the spectrum depends on the orientation of the optical transition dipole moment. So in order to calculate this photoselection effect, there's 2 types of information that you need to give EasySpin. So one is your photoexcitation geometry, so how your electric field vector of the light that you're using to photoexcite your spin system is oriented with respect to the lab frame. So that's kind of briefly shown here. So typically you would photoexcite along the y-axis of the lab frame, where the z-axis is the axis of the magnetic field, the static magnetic field, and the x is the axis of the V1 field. So, and then there are 2 different options. So the propagation vector, which in EasySpin will be called K, is along y, but you can have the electric field parallel, or in this case, perpendicular to the magnetic field, so to the z-axis of the lab frame. So that's one type of information that you need to specify. The other one is how your optical transition dipole moment lies with respect to the molecular frame, or in this case, the frame of the zero-field splitting interaction. So in order to do that, there's the new field TDM, transition dipole moment, where you can specify the orientation of the transition dipole moment. So you can do that, for example, by just specifying a single letter. So we want it to lie along the y-axis of the molecular frame, or you can use two angles to define it. So this would be equivalent to y. And this then allows you to define any general orientation of the optical transition dipole moment in your molecular frame. So that's the first ingredient. Then the second one is defining your photoexcitation geometry. So that's an experimental parameter. So this will be in the exp structure. And the way we've called this is light beam, where you can have two shortcuts, so parallel or perpendicular, or you can define the orientation completely generally by defining one k vector orientation and then an angle that relates the E field orientation with respect to the X and Z lab frames. So let's have a look at what we get if we simulate this. So first, I'm going to simulate the spectrum without any photo selection. And then we'll simulate it with excitation with the electric field vector parallel to the static magnetic field. And then we'll do the same thing for the perpendicular orientation. And then let's plot this. Okay, and then I'll also add a legend, so we know what's what. And then to make the explanation easier, I'll add a small plot showing the orientation of the transition dipole moment. Okay. So now we've defined our transition dipole moment cis TDM to lie along the y-axis, so as shown here. So that then means that if we select light beam parallel, so we have the electric field vector parallel to the magnetic field, we select molecules with the y-axis aligned with the magnetic field, as you can see here at the center. Whereas if we then use the perpendicular excitation geometry, we mainly excite molecules with X and Z contributions. So if I now change the transition dipole moment to the x-axis, this will change to mainly contribution of the X transitions for parallel excitation and of the Z and Y orientations for perpendicular excitation. Okay, then what you can also do is simulate what the spectrum looks like for an unpolarized light beam, which does not correspond to the isotropic excitation because you still have this propagation direction. You can see now that they're not quite the same. So this is also something that you can now simulate in EasySpin and take into account when you're doing experiments. Then one final thing, typically your laser isn't perfectly polarized. So you always have a contribution from isotropic excitation, for example, due to scattering. And in order to take that into account, you can use the field exploit scatter, which gives the fraction of the contribution that is given by isotropic excitation. So you can see that now there's more of the X and Z contributions even for the parallel excitation, because we've added 15% of light scatter. Okay, so I think that's everything I wanted to show you. Then I'll hand over to Matt for the next part.
All right, thank you, Claudia. All right, so just really quick, I wanted to get everyone on the same page about the second section, which is basically dealing with pair spectra. And the first part will be the spin correlated radical pairs. And a little earlier on, Claudia, had shown this general Jablonski diagram for a spin correlated radical pair, but I kind of wanted to just describe it very briefly before I talk about the actual EasySpin aspects of it. So for a spin correlated radical pair, typically, you're exciting a electron donor acceptor molecule, and then you get a charge separation. And this can really happen through sort of two different processes, either electron transfer or hole transfer. And this process, you're exciting basically an electron from one of the molecules up to some excited state. And since those two electrons were initially occupying the same orbital, they start out as an initial singlet state. And following electron transfer, that basically spin character is conserved and maintained, such that in this charge separated state, you're looking at basically an electron pair or a radical pair, which is sitting in a singlet state. And under the correct sort of spin interaction, spin parameters, the singlet state can mix with the radical pair triplet state, which then gives you a spin correlated radical pair spectrum that has sort of two absorptive and two emissive transitions, just sort of broadly speaking. This happens under cases where there's a difference in the G values of the two different spins, and then also in sort of a weaker coupling regime where the dipolar or the exchange coupling is on the is on the same order of magnitude as the difference in the G values. And given that these spins basically have this M sub S equals 0 character, either singlet or T0, on recombination of that radical pair to either a local triplet or back down to the ground state, on recombination of the radical pair to let's say a localized triplet, it ends up conserving the angular momentum, and you only ever populate the T0 sublevel of that of the radical pair. Okay, so very, very brief overview, and I'm going to switch to MATLAB and talk to you a little bit about how we actually go about simulating a radical pair. So I'm going to start off at much higher magnetic field than we've been showing, because I think this is a really nice example that we demonstrated in the paper, which is of the bacterial photosynthetic reaction centers. So we're going to work at W band, so we get some nice spread in the G values of the radical pair. And let's see, defining the experimental range. 5 to 3393. Okay, so for a radical pair, you need to sort of consider the two different radicals that we have present in there. In this particular system, we've got basically a chlorophyll radical and a quinone. So I will define for the chlorophyll, the spin, so it's a spin 1/2, and we have a G value of, let's see, it is 2.023. And so for radical pair spectra in general, it's super helpful to do your best to identify all of the contributing components to simplify the simulation. And so in this case, we've got the chlorophyll. Just do, well, line with PP, 0.3. And then we can do the quinone. U dot S is going to be 1/2. Q dot G going to be 2.066, 2.022, and its corresponding line width, which I will leave as the same. In a radical pair system, and then we want to many cases are in your radical pair spectra, the line widths may actually not be the same. And so you can separately include your nuclear spins, or if you want to include differential line widths, you can actually include that by using G-strain as a way to estimate different line widths between your spin components. Okay, there we go. And then we forgot that we need to change the harmonic because we are typically dealing in exp.harmonic equals 0. So that would be your field detected, and here's your sort of your absorption spectra. Okay, so this is your two components of this the radical pair. Now we actually want to get into the radical pair part of it. And so we are going to define our spin system, S dot S, and you can either take the spin dot S, C dot S, space C dot, or Q dot S, or just define these as both spin 1/2, because we already know what those are. Then we can take the G values of the two spin systems that we have, and we will, in this case, I will basically copy the G values that I have provided above, just to help speed things along. Okay, and you can't, like I said, you can't provide two different line widths, so they basically have to both have the same common line width. Okay, so this is the basic spin system. Now it's a radical pair, so there's going to be some interaction between the two. In the bacterial photosynthetic reaction centers, the exchange coupling J is effectively 0 in here. That's not going to give you really an interaction between the two spins, but the main driving interaction is actually the dipolar coupling. So we can define that as cis dot dip. And this is about 2.3 megahertz. And then we have to define the initState. So for radical pairs, we've actually provided a simple shortcut where you can basically say singlet state, and that this gives you the initialization state of a singlet, which is what should be present here. Okay, so now you run this and you can pull out your radical pair spectrum, which has both sort of absorptive and emissive transitions across the length of the spectrum. In this particular example, I'm kind of neglecting a few of the differential orientations, but I can start including those in now. So because you're dealing with two different spin systems, you have to sort of define your molecular axis and how your various spins are oriented relative to one another. And in this particular case, we are going to take our quinone and say that will define our molecular axis, and we're going to instead rotate both our we are going to rotate our chlorophyll and our dipolar coupling relative to that. So in this case, they pulled it from the crystal structure. They were able to pull out some approximate orientation information, and then so that defines the Euler angles for the chlorophyll. And like I said, we are defining it relative to the quinone, and so we'll set those both to 0, and then our cis.EE frame, and we are going to rotate our dipolar tensor relative to the quinone also. So minus about 68, minus 71, 0. And then what I forgot is that I put in degrees, and these should be in radians. So times pi over 180. And you see some subtle spectral changes occur in the spectrum to account for those different orientations. And lastly, let's just do our output just to look at the separate spectra. And so one of the things that you'll see is that in this overlap region, you get a little bit of change of the spectra gets a little kind of perturbed because due to the mixing between the various between the two different spins at that point. So it's not just radical pair spectra are not just simply the two different spectra sort of added up. There's additional mixing that occurs in our radical pairs. Okay, so that's our that's for the basic radical pair spectrum. And now when this guy recombines, you get the case where you have to populate your basically your T sub 0 spin level. So for a basic triplet, in the T sub 0, we've actually included again another little shortcut because this is a sort of a common occurrence. I can use I should probably do this at a different field because that is where the spectra was acquired. And then our trip dot initState in this case is going to be T0. And this spectrum is going to look significantly different than the spectra that Claudia had shown earlier. Namely, you get sort of an absorptive and emissive across the spectrum. And just kind of a point to make is that the T0 populated spectrum, you can't ever get the same line shape of a T0 that you can get via the intersystem crossing and population via the XYZ or zero field spot states. Okay, and so that's radical pairs. Do we have sort of very basic intro to some of the radical pairs, and there's recombination. I will move on to a different pair spectrum, which mirrors radical pairs quite a bit, and has been a relatively new topic of discussion, which is singlet fission. All right, so radical pairs, and then we've got singlet fission. And so again, this is the same figure that Claudia had mentioned earlier. And for those who are not familiar with singlet fission, the basic idea is that if you've got a pair of chromophores whose triplet energy, the level of their triplet, is half that of the singlet state, such that the energy of basically the singlet state is equal to two triplets. Under the right circumstances, your system can undergo singlet fission, where you basically go from this excited singlet to generate a pair of triplet states, which occur which come out in, again, because the initial pair of electrons were a singlet, this triplet pair state also occurs in a singlet state. And due to the basically fine structure interactions between the two spins, you can get further mixing of the singlet state with the quintet state. And that basically selectively populates, for the most part, the M sub s zero, M sub s equals 0 state of sublevel of the quintet. You can have further evolution where these two spins basically walk apart and are no longer coupled, leading to sort of a pair of uncorrelated triplets at sort of long times, or depending on the material you're looking at or the system you're looking at, you can end up here in a variety of different ways. But due to conservation of angular momentum, you start M sub s equals 0, and your triplets also are also populated in their M sub s equals 0 state. Okay, so let's go back to MATLAB, and I can show you just a quick little example of what's going on here. So I'm going to let's put on some experimental parameters. Okay, so let's define initially a triplet state. So we'll do sys.t sys.t.s. So define our initial triplet states. We need to provide the zero field splitting for that triplet state. And in this case, I'm going to take as an example TIPS tetracene, which is more or less axial. And I don't remember what the megahertz, so I'm going Tesla to megahertz. It's about 50 megahertz or 50 millitesla. And we are going to do Okay, so here's our basic triplet. This would be your long-lived triplet in the system. And for that, we need to define the init state. We can either do, so we did this as, so we can have this basically T0, again, as a quick shortcut, or if we wanted to kind of jump in as a different example, we can use our define a population vector in this case, the eigenbasis. So this would be your population in the eigenbasis. Okay. And then we are going to pass these guys to Pepper. Just to EXP, and there that gives you your basically tetracene triplet spectrum. And so this is just again, like I said, it's just the triplet. And in principle, so for singlet fission, it's a pair of these triplets interacting, and that gives us sort of two ways. There's SPC. There are kind of two ways we can think about this. We can either treat this as a pure quintet state, so as a sys.q, as we can treat it as a pure quintet state, or sort of a little more true to the system, we can treat it as a pair of coupled triplets. And so if we were to treat it as a quintet state, you would have to use sort of an init state like this, but taking into account the sort of the full quintet levels. But I'm going to go with the basic pair of interacting triplets, and sysq.d. And so because we have again, it's a pair state, we want to use what we have above, .d, for the triplet. Okay, we can provide it a line width, just WPP 5. Well, keep the same one, 0.8. Okay, then we need our coupling between the spin states. I'm going to neglect the dipolar coupling, and in this case, just provide a rather large exchange coupling, which is common in these systems. And we're going to do about, in this case, about 30 gigahertz. It's 10 to the 3. Okay, and for our just q dot init state, because we are solely populating the quintet m sub s equals 0 state, we need to list out a whole bunch of energy levels. So this ends up corresponding to your singlet, your T minus, T0, T plus, and then it would be Q minus, minus 2, Q minus, Q0, Q plus 2. And that should be in square brackets as a population vector in the eigenbasis. And then if we run this, what we pull out is our we can see our triplet spectrum out here, and then in this sort of narrower region, which ends up being the zero field splitting divided by roughly 3 is the quintet spectrum that corresponds to the quintet from singlet fission. And just kind of a word of warning when dealing with the eigenstates, if we were to look at if your exchange coupling is small relative to sort of the overall interactions, you actually may get a lot of mixing between the various states, and your spectrum can start to get a little start changing a little bit, because you've got different mixing of the states, and you have to be very careful, cognizant of what your sort of overall energy level diagram looks like. Okay, do we have any more questions that I might need to answer for this? Ordering from low to high using EIG, which magnetic field does it assume? The order may change at different fields, and that's exactly right. The ordering will change at different fields, and unfortunately, which makes life probably far more difficult for people, is that the ordering of this initState basically is at each field. So if your energy levels are flip-flopping as you move through the magnetic field, these populations here will flip-flop as you move through the field. One way to get around that is to sort of, you can use basically you can potentially define your spin state in terms of in the coupled basis or as a full density matrix, and that will I think that's one way to sort of avoid these problems. Or we go back to the shortcut, which is just to assume this, instead of a pair of coupled spin states, you deal with just a quintet, and you treat it as a pure quintet, and then you don't have to worry about the triplet pair states mixing in or overlapping with your quintet states. So hope that mostly answers your question. Okay, so let's get back to talking about the ordering really quick. So we are going to show here is our pentacene spectrum. Now, some of you may be familiar with with the experimental parameter exp dot ordering. There are built-in functions for this, which treats it as basically a distribution, either parallel or perpendicular. So you can basically go from some value, some positive or some negative value. I would say look in the documentation to get a better idea of what the ordering is doing. Let's see, let's change this a little bit so we can see what is happening a little bit better. Okay. All right, so exp.ordering. So this basically provides you a way to, if you're dealing with an ordered sample or ordered film, you can get sort of a distribution or selective distribution of the range of components present in your sample. So where you can sort of say it's ordered with ordering of a positive value, you're selecting sort of the Z component, Whereas if it's some negative, it would be basically the perpendicular to the magnetic field versus sort of the parallel component. But the new feature, the one that I wanted to really talk about or draw your attention to, is going to be this. We will put these both as the same. It is called sample rotation. So if you do exp dot this would be if you have for instance, if you have a film and you're going to be rotating it about a given axis in your spectrometer, we can choose, say, let's just do pi/2, and we want to rotate this about some axis, say the molecular X axis. So you rotate it 90, so you've got your film, which was initially oriented such that you're only sampling the Z component. If you were to rotate it, now you're suddenly sampling what would be the Y component of the spin system. So if we were to, and you can arbitrarily do these rotations about basically, and by any amount or about any axis. And this is kind of an extension and an improvement with respect to the ordering parameter within EasySpin and how we can treat the spin system and rotate the spin system around. And that's really the last little new feature that we wanted to share with you. Any more questions for either myself, Stefan, or Claudia? And I guess I can give maybe the final words to Stefan if he wants.
Well, thank you, Matt, and thank you, Claudia, for presenting this and actually for implementing this in EasySpin. It's pretty powerful and cover a lot of things. For all attendees, thanks for participating. If you have questions, speak up now or raise your hand or type in the Q&A chat. We'll be hanging out for another couple of minutes. For those of you who have no further questions, thanks for attending. Keep an eye out on easyspin.org for new versions. The final official EasySpin 6 release should be out sometime this year. And please also join on the forum if you have questions. One in particular is that if you have answers to those questions as well, please help out so the entire community benefits. Thanks for participating and have a good day or a good night.